Good time of the day, everyone. This is Ivan from EPIC, the European Photonic Industry Consortium. And today you're watching the EPIC online technology meeting on quantum metrology and quantum sensors. We have a very impressive agenda for today, as we will hear from 7 representatives of the quantum industry, starting with Katrin, the CEO of Bosch Quantum Sensing, and Vincent Menoret, the head of Inertial Quantum Sensors R&D at Exail, followed by Andreas Schürzinger, the sales lead at Qant, and Jonathan Steckel, the technical fellow and director of advanced technology imaging at STMicroelectronics. As well, we'll hear the presentations of Nordmann, the product manager at Qnami, and Devang Naik, quantum expert at GLOphotonics, as well as Enrico Casamenti, R&D engineer at FemtoPrint. Apart from these 7 wonderful presentations given by 7 companies in the value chain, actually there's over 160 representatives from the quantum and photonics industry in the room today with us. And every level of the value chain of quantum sensors is actually represented, starting from the R&D. We have a big team of R&D institutions and universities present, people working in microelectronics foundries, with materials, with lasers, with optics, equipment manufacturers, system integrators at different level, many companies just working on the photonics technologies themselves, as well as end users from the automotive, from aerospace, from consumer electronics, and others. This will be a very exciting event, and I encourage all of you also to exchange your opinions in the comments, as the aim of this event is also to build a strong network in Europe on quantum technologies. Before switching to the presentations, I would like to say that this event is done in partnership with Laser World of Photonics and their new event dedicated to World of Quantum. And this event is also sponsored by PI Imaging. Just a few words about those. The World of Quantum 2023 is an event that will take place during the Laser World of Photonics in Munich, June 27 to 30, at Messe Munich. And the key topics will be the quantum funding politics and marketing insights, as well as computing and quantum simulations, quantum communications, quantum imaging and sensing, photonic enabling technologies, and quantum education and the career. So feel free to join this event. You're all invited by Messe Munich and the Laser World of Photonics, as well as by EPIC. And just a quick introduction of our sponsor, the PI Imaging. It will be actually done by the CEO of this exciting company. And I'll give the word to Michael, please.
So Ivan, thank you very much for the introduction. So we are very proud to be sponsoring this event. Of course, quantum is a very broad spectrum, and we are specifically positioned in the quantum photon detection. So we do build detectors which can count photons, detect single photons. Our technology is based on single photon avalanche diode SPADs. I think they became very popular in the LiDAR field, proximity field specifically. So in this slide, you can see a few figures and nice micrographs. I do not want to dwell too much around them. You will also be able to check out the slides later on. So just if you have any needs for quantum light detectors, reach out to me. We can improve your image quality and give you a very good timing resolution.
Okay, thank you very much, Mikhail. Here on the screen, you can see the contact details of PI Imaging. So feel free to outreach if you're looking for some single photon detectors. And without further delay, I would like to introduce the first speaker of today's event, Katrin, the CEO of Bosch Quantum Sensing. And Katrin, whenever you can, please feel free to start your presentations. Okay, now it's coming. I'll just put it in the full screen mode and you're good to go. So Katrin, apart from introducing the efforts and the latest developments on Bosch, she will just guide us into a little bit into the topic of quantum sensing, giving a little overview of the whole field. Okay, now we're good to go. Katrin, the floor is yours.
Thank you very much to all are sitting here. I heard there's more than 100 participants we have, and today I will like you to tell what is Bosch doing in quantum sensing, create the unthinkable, the power of quantum sensing. Just make a breath, close your eye and imagine you are sitting in a park in front of a hospital and a little girl drives in with a wheelchair, and after a while you see her walking or even jumping through the park without any crutches. Is this not fantastic? It's a pity, but today we are not so far yet. However, in about 20 years or something, this should be possible with quantum sensors. Then we will be able to measure brain signals and transfer it into mechanical actions. So we can control, for example, artificial limbs or only with our thoughts. However, until then, a lot must be happening. For me, 3 factors are essential. First of all, visionary thinking. Second, agile and persistent acting. And third, excellence in market and technology. And for Bosch, innovation is no coincidence. So let's start with visionary thinking. Already 10 years ago, our Bosch Corporate Research Department launched first scoutings and studies. And years before, everybody was talking about it. And finally, in 2021, a functional prototype was set up in corporate research lab. And this sensor was so extremely sensitive that the prototype can measure magnetic fields which are 1,000 times more sensitive than current MEMS sensors. I know it's difficult really to visualize magnetic fields, so I try to explain it with the extreme sensitivity by the using of sound. Can you hear this helicopter? This is the picture of a MEMS sensor, the noise of the helicopter. And now, if you hear this, the noise of a falling snowflake, do you hear it? No, of course not, because you are not a quantum sensor. But this shows how sensitive quantum sensors are. So this is really very, very important. And this sensitivities offer us a huge variety of new applications. But first of all, let's think about what are the USPs of these magnetic field quantum sensors. They are extremely sensitive. They are in principle much smaller. They have a higher spatial resolution. They have an extremely wide measuring range. They can provide additional information. And they are robust and calibration free. And this makes the new generation of quantum sensors so unique. And this was also the reason why Bosch management decided to commercialize this sensor, which was built up in the laboratory from CR. And then was the question, how can we commercialize very quick this kind of sensor? And they decided to build an internal startup. And this internal startup combines best of 2 worlds. On one side, we are flexible like a startup. And on the other side, we have the power and the network of a corporate company and we can work with all the flexibility at the same point as with the power of a company. And this is the best starting point you can imagine to commercialize quantum sensors. Fast and open-minded, we are looking for the pain points of the customer and to understand the real value added of quantum sensors. We have been working very, very intensively since the beginning of last year. And it's not easy because there are a huge range of application fields. And you can start with medical applications. There you have the mobile magnetocardiogram, or you can control prostheses. You can go to the consumer goods. There, for example, is an application heart monitoring of drivers or PCI game controllers. If you come to exploration and navigation, you can use quantum sensors for exploration of mineral resources or for airplane navigation. Or you come to process improvements. Quantum sensors you can use for non-destructive material testing or for battery control. And because quantum sensing has so much many applications, it's really important to find the right one. And therefore, we build up systematic funnel management. This ensures really that we get the best business cases. And this funnel was started from the Bosch innovation process, but we adapted it to the requirements of our startup and the total new field of magnetic measurements. And therefore, we increased the idea generation phase. So at the moment, we are really looking, we're trying to get a lot of ideas. And then we have a next phase where we make an individual idea evaluation with a use case selection framework, which was developed from us. And in the next step, then we start with the qualitative validation and the quantitative validation. And what is important is that our approach has a lot of milestones, so that at each milestone, we stop and decide whether it's the right application with a real scaling potential, because we are only looking for ideas which creates a real Wumms, as we call it in German. And also our approach is highly iterative and user-centric in order to increase the maturity of the assessment and get deeper and deeper insights about the technology and the market and the customer. So the most promising use cases move from phase to phase until a great idea came out and we can use it to scale. And after each phase of decision, a decision is made whether it's worth to continue or not. And then we start with the incubation and the piloting of the piloting and incubation of the idea and the scaling. And to get all this done, we also need to be really good in the technical excellence. And if you look at the laboratory set in 2021, we can improve it in the first year to a shoebox size. And now we have already the box at the size of a milk box. And this technical excellence is necessary to quickly turn the lab sensor into a small, robust, wearable sensor. With this sensor, we are able really to check with the customer whether the idea has a real customer added value for the customer or not. And with each new application, we learn more what is needed to maintain market leadership in quantum sensing. And now, we as a startup, we really believe in the vision of the jumping child. With our excellence and highly motivated team, we work hard and persistent on market and technology. So the day that you can control things only by your thoughts will come closer and closer and closer. Thank you very much.
Thank you, Katrin. Thank you very much for your talk. Very inspiring one. And I'm sure we'll have a lot of questions in the audience about this. Yeah, starting from now, the session is open for questions and answers. Just please use the raise hand button at the bottom of your screen if you have a question for our speaker, and I will pass you the floor. We actually have already one from Jeremy Gibbon. Please, Jeremy.
Can you hear me?
Yeah.
Yes. So hi, Katrin. Thank you very much for this presentation. I have a question. Do you have challenges in getting your devices, specifically the resonators, actually in your sensors? Because you showed us the internal startup funnel and the challenge in getting the applications, but how about building the sensor?
As I already show you in this picture, we are reducing the sensor step by step, and our goal is to get a sensor this has the size of a matchbox.
Thank you.
Yeah. Okay, I hope that answers your question. Anyone else? I actually had a question myself, Katrin. So you introduced several potential applications for this magnetic field sensors. Do you have in mind already which one would be the killer application that would allow to bring it really to the market?
We have a couple of killer applications in our mind, and our clear view is that on long-term base, brain-computer interface will be a real huge market.
Okay, that's great. And if you can continue a little bit your presentation, saying by answering the epic question, actually, what the community could do for you and what you can offer to the community here.
I think for the community, it is really important to work very closely together, because the ecosystem has still to build up, and everybody is necessary to invest a little bit in this technology, that we will keep the leadership in quantum sensing in Europe.
Okay, yeah, that's very clear. Thank you very much again, Katrin. I think this was very clear for everyone, this nice introduction into the world of quantum sensing. And with this, I'd like to pass to the second speaker of today, which is Vincent Menoret from Exail, the head of Inertial and Quantum Sensor R&D. So Vincent, whenever you're ready, please share your presentation.
Yes, hello everyone. Can you see my presentation?
Yes, you're good to go. Thank you.
All right. So, well, thanks a lot for the opportunity for us to show you what we are doing in the field of quantum gravity sensors mainly. So I'm Vincent Menoret. I'm from Exail, and some of you might know us under the name of Qant, which is the company which was started more than 10 years ago as a spin-off from two French laboratories. 2 years ago, we were acquired by IXBlue, which is a French group, a high-tech French group. And then the name changed a few months ago, and we became Exail. So this is our new name, but it's the same team for now more than 10 years working on quantum sensors. And Exail is a now mid-sized French company. It's 1,500 employees. We have offices all around the world, but all our R&D and production is done in France. As the quantum sensors division of Exail, we are specialized in high precision measurements and quantum sensing and metrology, especially with cold atoms or cold atom related applications. We started, as I said, 10 years ago, meaning that we now have tens or even hundreds of systems in operation all around the world. So it's not only saying what we're going to do in the future, but we already see ourselves as quite mature in the field of quantum sensing because we started so long ago. And our products are divided into 4 main categories. So today I'll be giving you a few examples on what we're doing with our cold atom gravimeters, but we also build atomic clocks. We're also involved in high precision frequency transfer. And we also build lasers and subsystems for other types of applications, for example, quantum computing. And actually, this is one of our strengths at Exail, is that we have a vertical integration model, and we can manufacture everything from components to full instruments. So if I take, for an example, the gravimeter, which is shown on the right, or can be the quantum computers made by French company Pascal, to which we supply the lasers, well, we're able to make like big instruments. We can make the laser system and all the control electronics and software that goes with it. And we can also manufacture all the subsystems that go in there. So we have like micro-optical benches, which are necessary, some fiber lasers, and all the way down to the components, because we make ourselves like specialty fibers and modulators. And it's really important for us to have this like vertical integration. And this is really key to making such complex systems work on the field. So a few words about our gravimeter. Well, it's basically the same principle as Newton almost 4 centuries ago, dropping a mass and measuring its acceleration, except that we're not dropping an apple, we're dropping a cloud of laser-cooled atoms. And the challenge is basically squeezing a lab experiment like you see in the middle, which is a picture from the gravimeter at Berkeley, something like 10 years ago, into an apparatus which is the size of a suitcase. And on the right, you have a picture of our instrument from 2 years ago. So this is really the challenge that we had to face. So huge technical integration challenge without, of course, sacrificing on the performance and keeping the very high level of performance offered by quantum systems, as we've heard from the previous presentation. And being able to master all the optics and photonics was really key to succeed in this challenge. And in particular, you can see we work with what's called telecom laser technology. So we are able to master all the assembly and manufacturing of these systems, and also free space micro-integrated optics that go into the gravimeter, and which also goes into our clocks and into all the laser systems we use for quantum computing, for example. And this is how we can make these instruments operate on the field. And well, we've demonstrated recently that it can work in really harsh conditions. So this is a few examples from a European project where we put one of our quantum gravimeters. So AQG here on the top stands for absolute quantum gravimeter. It's been installed in the summit zone of Mount Etna for now almost 3 years. And the conditions are really hard. You can see there's a lot of vibrations due to the eruptions. There is snow in the winter. We're used to having no power during several months in the winter because of the snow. There's some acid gases coming out, temperature fluctuations, and so on. So really a huge challenge for a quantum instrument that, only 10 years ago was confined to laboratory environment. But it turns out that other competitive technologies based on classical technology are actually even harder to operate in these environments. And at the end, all the effort we've put into integrating the systems seems to be the right way to go. And we've demonstrated that despite all these challenging conditions, we could have a state-of-the-art performance in terms of measurement and of create some added value for end users like geophysicists to understand what's going on in the volcano. And this shows really the industrial maturity of all our solutions. They can operate on the field, and we show that quantum sensors, they really have a role to play to bring sort of a kind of quantum advantage in the game of high precision sensing and metrology. And with this, I'd like to say a few words to end this short presentation. I hope that I've convinced you that with now 10+ years of experience in both photonics and quantum systems, we've been able to bring cold atom quantum sensors from laboratories to the field and operate them in real life environments. And I think, in my opinion, one of the main reasons we can do this, besides from being able to do the physics and the metrology, is because we can build ourselves all the components that go into the system, and this is really key for us to like have the right specs for every component in the system. Of course, it's not finished. We have many innovations in the pipe. We are working with the space agencies to qualify our lasers for space quantum systems, space quantum accelerometers. We are working on onboard quantum sensors. We want to put them on ships and on moving platforms. We have a project where we're going to work on an autonomous device that can perform gravity mapping with applications to geophysics, reservoir monitoring, inertial navigation, and so on. And of course, a lot of R&D going on in the field of photonics to improve all these quantum instruments, all the range from quantum sensing to quantum computing. Basically, all these need optics and photonics, and we have several developments that are going on in the field. And of course, well, we are always open to new partnerships and collaborations to identify new partners to push the technology further and further. And with that, I'd like to thank you for your attention and for the opportunity to present you what we're doing.
Thank you, Vincent. You have touched a lot of very exciting applications in your presentation, I would say. So everyone, yeah, please feel free to ask questions now. Just use the raise hand button, and I will pass you the word. Let's start with a question from Marco from Coherent.
Yes, good afternoon. Can you hear me?
Yes.
Yes.
Okay, thank you. First of all, thank you very much for the very great presentation, very interesting. So coming from the laser industry, one of the things that leave us a little perplexed, and by the way, I should say that Coherent is partly participant to the quantum ecosystem as we sell lasers. But one of the things that leave us a little bit confused is the huge variety of different atomic systems, especially if you look at quantum computing, that makes it difficult to understand if there will be a standard on the type of atoms of ions or on the type of laser sources required. So my question here, you are developing gravimeters, so is a spatial niche area. What would you say about the maturity of laser sources for gravity sensor? Do you think that they're mature enough? Do you think that the systems have been selected and either cesium or rubidium, or you think it's still an area where there is a need for drastic improvements?
Oh, that's a very good question. I'd say that for sensors, the community has like kind of converged to the use of rubidium atoms, and meaning that we know that we need to develop laser systems at 780 nanometers. There are, of course, in research labs experiments with other atoms, but these are much further down the road from applications. It's still fundamental research using strontium, for example. These experiments are really complicated. They need tens of wavelengths to operate. So maybe one day they'll come to more like market applications. But like in the coming years, and at least in the field of gravity and inertial sensing, it looks like rubidium is now the best candidate, and also because the laser technology is really adapted.
Thank you.
All right, thank you. Now Kati from OIPT, please go ahead.
Sorry, I think I might have accidentally hit the button there.
Okay, no worries. So you don't have any questions?
Sorry.
Everything's clear? Okay. Then we go to Edmund from Cambridge Consultants.
Yeah, hi, I'm going to steal your question, Ivan. So gravity meters for volcanology and geology, very interesting, but I'm guessing this isn't the wide-scale killer application which Exail is aiming for with your gravity sensors. What do you see as the big market opportunity of this technology?
Well,
or am I wrong about the gravity sensors?
No, you're right. The way we've been building this is going step by step, and like we're not like saying we're going to sell like thousands of them every year. So gravity in itself is still going to be a niche market. The way we see the expansion is, of course, all the resource monitoring. It can be a huge market, can be from like anything from oil and gas, but which is maybe now not the main research area, but carbon sequestration is one of them, which could be monitored through gravity. And also, as I said in my last slide, we're looking at inertial navigation, where atoms could help to improve the quality of high-end navigation systems. So that's the kind of range of applications we're targeting.
Thank you. Okay, and well, last question for you, Vincent, from myself.
Sure.
As you mentioned, even though you're a vertically integrated company, meaning you have all the components available that you need, is there still something that the community can help you with? The people that are now in the audience.
Yeah, sure. So yeah, we are a vertical integrated company, but there are some building blocks which we don't have right now, and which we think can be useful to build the next generation instruments. So, for example, we have a European project which has just started, where we're working with Asfericon to build specially designed beam collimators. So we are really open to like new building blocks for our instruments, and we're always on the lookout for new good ideas and new technology. So that's clearly the case, yeah.
Okay, and if you can help Exail with this solutions, I guess you're welcome to reach out to one.
Yeah, exactly. I don't have like specific needs right now in mind. There are plenty of things we have in mind, but no specifics right now. But we are completely open for discussion, of course.
Okay, that's great. Okay, so thank you again for the presentation. With this, I'll pass the word to the third speaker, Andreas Schürzinger, the sales lead at Qant. And Andreas, whenever you're ready, you can open up your presentation.
Sure, thank you very much. Good afternoon, everybody. It's really great to be here. I have a few slides. I'm going to tell you a little bit about what we do as a company. Let me start off by saying I have a bit of a background in sensing technology, industrial sensing technology, and I came to this specific field about 2 years ago when the company Qant was already 2 years old. We're about 4.5 years now, and I've yet to come across an industry or an industry segment where it's super technically challenged and advanced. And of course, you guys all know about this because you've been doing this for so long, but are equally at the same time keen to find market applications. And we can make a little count of how often we're going to hear the word killer application this afternoon. Super interesting and I think super encouraging also, especially if you come from a technical sales background, to know that everybody's thinking about how can we get this to market. And I won't be able to give you a killer application. I can explain to you how we try to get there. And let me start off by saying what we are about, what the company is about. So that's our company claim, revolutionizing the quality, how machines analyze the environment, how people notice information, and the way humans think. And now, apart from this being a nice play on the initials of our company name, it's a bold claim. And the first time I heard it, I said, wow, can I identify with that? Changing the way how humans think. And but if you think about it a second time, is we're introducing a lot of new approaches, a lot of new things, not the least in quantum computing, and excuse me, also in quantum sensing. So I think it is actually valid to say that somehow we need to adapt to what we're bringing here to the market and the way we think about technological solutions, but as well as about the applications. Just a few words on our company. We're part of the Trumpf group, well-known German machine builder, and like some of the companies here, we spun out of the corporate brains, but we've grown quite a bit. We have 65 people today, looking to grow to about 100 by the end of the year, and our product developments, to put it very short and crisp, is 3 different sensors in one chip. We, apart from the funding we get from Trumpf is our 100% owner. We are also publicly funded within the range of several projects, and I'm going to mention a few of those. And these are the 3 sensors that we're working at: particle metrology, atomic gyroscope, magnetic sensing, and photonic computing. And I've also listed a few of the applications. Now I'm with the part I'm running in Qant. We're about 11 people focusing and concentrating on the particle metrology. And the reason why we have this here is the first on the leftmost side is that's where we're most advanced with the product development, our technology readiness level. We're seeing applications in chemistry, in pharma, in food processing. They're super interesting applications. I'll give you an example of those. There is applications for the atomic gyroscope. We're in a DLR project, a publicly funded project related to satellite leveling or satellite control. We're working on magnetic sensing, and you can see some of the participants listed of those projects that we're in at the bottom. Prosthesis control was already mentioned. That seems to be a very interesting but very challenging application. And nonetheless, not part of this event this afternoon, we're working on photonic quantum computing, and that consumes a lot of the resources within our company. And obviously has also a lot of challenging, but there's also a lot of promises. To tell you a little bit about what we do with this device here, with this particle sensors, you can have a guess at the size, scale of with the pen. It's about a shoebox, slightly larger than a shoebox size. And the way we go about finding applications for it is not so much strategizing, not so much taking it step by step, but at some point we had to say, okay, now we need to get it built and we need to ask potential end customers. And that has been very much the approach. We've been making a little noise about this for about a year now. And we've been working with our pilot customers, early adopters in the industry, specifically chemistry, specifically biotech, and trying to eke out those use cases that we see that it's fit to. Just a few words. It works with polarized light. It does some really clever things with superposition of polarizations. And the nice thing about it is, and that's our promise to the industry, is not that it goes much finer grained into much smaller grain sizes than currently available instruments, but it gives you more parameters, more measurement data with every shot. And that means you can play a lot with this information. And that's what we've seen has sparked a lot of the interest. So one of the promises is that you can do shape recognition, or at least shape classification with the instrument without actually taking photos, without using cameras, without processing a huge amount of data, but by training a neural network based on the signal results that you get from our system. And the center use case was the one we started. Can we distinguish elliptical from spherical particles? And it turns out, yes, we can, using this machine learning approach. And then almost immediately, people from the biotech industry said, well, can we use this to actually control bioreactors to get a direct measurement of the happiness of the organisms that grow inside these reactors? And the interesting thing is, yes, again, we can do that when these organisms, in this case, it's chlorella algae, when they grow, they split, the cells split, and that is a shape detection, a shape change that you can monitor, and that's immediately tells you something about the vibe, about how lively the particles are, how well they are procreating. For us, they are just particles. They have a certain shape. For the biologists, that is vital information that is not indirect, but is direct. Indirect, they get all the time, temperature measurement, O2 saturation, salinity of the bioreactor. But what was interesting to them is to look at the actual, for us, particles, for them, organisms and things that help produce. And there's also a green promise in that. So it fits in really, really well with changing the way humans think about quantum technology and think about this approach. So that's why I like it a lot. And again, our approach has been go to the market, get some of those early adopters on board. They're all investing just as much time as we do, but it's super interesting talking with those people and getting their feel for the killer application. So let's see where this leads to. We're at several trade shows this year. At Hannover Messe, we'll be at PitCon, which is a chemical trade show. And of course, we'll be at Laser World of Photonics in the Quantum Show in Munich. So hoping to see you there. And that concludes my talk already. Thank you very much.
Thank you. Thanks to you, Andreas. That's a very clear presentation of Qant activities. Yeah, now it's open for questions. Please push the raise hand button. In the meantime, I'll ask Andreas as all the previous speakers. Andreas, what could the other members of our photonics community do for you?
So we do have a vertical integration, just like was explained before. But again, we use a lot of components and we do a lot of networking with the industry. So lasers is always a problem. Lasers at funny wavelengths. That, for example, the biologists, they want to create the luminescence based on chlorophyll, so they need blue light. Blue lasers that are stable, that are wavelength stabilized, that have a narrow bandwidth. That's an ongoing quest that we have. As one example.
Can you give specific wavelengths that you want and specific line widths?
So we're working with a telecom laser at 1550 at the moment. That is very stable. That's technology that's been around. And the blue light, we're looking at 405 or 450 nanometers. That we'd be interested in. And we have some solutions. It's just about scalability of those. Yeah.
Any uses at 650, 750, 850, 950? Any of those, in the short wavelength infrared windows, but still very narrow line widths of kilohertz to 10 kilohertz, very stable.
But potentially, yes. Yeah. Okay. Right. I'm on the other side of things, like selling to the market. But I'm happy to get a discussion going. If you just hit me up with your contact details, that'd be good.
Yeah, Frank and Andreas, please feel free to continue your discussion in the chat if you would. And if there is no other questions, I will pass the word to the next speaker of the session. And it's a very special presentation of today. We have covered quantum magnetic sensors, gravimeters, and now also particle shape sensors. So Jonathan Steckel, technical fellow and the director of advanced technology imaging from STMicroelectronics, will talk now about quantum imagers.
Yes, hello.
Hello, Jonathan.
How are you?
Let's see if you can share your presentation with us.
Yes. How is that?
Perfect. You're good to go.
Excellent, great. Yeah, so I'm Johnny Steckel. I'm at STMicro in Grenoble, France. And what I'm going to tell you a little bit about today is the technology that we've been working on for the past several years that's based on colloidal quantum dot technology. So I don't have a lot of time, so I'm going to go through some of these slides pretty quickly. So what we're dealing with here is basically it's a colloidal synthesis. It's a solution process. We synthesize semiconductor nanoparticles in solution, and they're a couple nanometers in size, and they have organic molecules bound to the surface to keep the planes of these particles passivated and keep trap states at bay. And it's essentially leveraging quantum confinement. So as the semiconductor shrinks down to the nanometer regime, we're leveraging the fact that we're in a quantum confined region, meaning that the exciton Bohr radius of an electron and hole can't spread out to its full radius. Instead, it stays confined into that small particle. We get discretized band states, or discretized states at the band edge. And we also increase the amount of light we absorb per semiconductor volume, which is a really nice benefit. So we make thin films of these colloidal QD particles, and these right now the technology is based on using a sulfide semiconductor, and the film is densified, baked to make hundreds of nanometer thick colloidal quantum dot films that absorb light in the visible, near IR, and SWIR region of the spectrum. So what we do is we build up a photodetector stack based on a film of colloidal quantum dots in the middle, and we build that photodetector stack, which consists of bottom electrode on a copper via. The copper vias in the CMOS below define the pixel pitch and the resolution of the image sensor, and do all the readout and provide all the circuitry to create a high resolution, silicon-based image sensor. But with the photodetector stack on top, which we coat over the entire area of the wafer. So this is now scaled up to 300 millimeter silicon CMOS wafer. The copper vias define the pixel size and pixel pitch. We have a top electrode that's metal, an electron transport layer, the quantum dot film itself, a whole transport layer, and then the top transparent electrode. And we use an anti-reflective coating to boost our quantum efficiency and get more light down into the quantum dot film, micro lens array as well, and then encapsulation. We have ourselves an image sensor. So what we're currently making is something around 2.3 million pixel pitch. The resolution is around 1.6 to 2.2 microns. What we're looking to commercialize first will be a 2.2 micron pixel pitch, 2.3 megapixel image sensor using lead sulfide based colloidal quantum dots. And from a cost perspective, it's kind of a paradigm shift, I would say, in terms of creating image sensors that can detect in the SWIR region, the shortwave infrared region of the spectrum, because it's relatively cost effective. We're doing this on 300 millimeter CMOS. So from a cost perspective, the QDs, the spin coating, the technology itself is relatively low cost. And so in the end, from a sensor per chip cost, we're looking at similar pricing to what you would expect out of a current silicon-based RGB image sensor, for example. But what's cool, it's 100% fill factor photodiode over the whole area of the wafer. And it's a global shutter pixel, so we can shrink the global shutter pixel size down to these really great low resolutions. And the quantum efficiency at the first absorption peak and for most of the spectrum is quite good. And the first absorption feature is defined by that absorption into the first band edge state. So we see really good quantum efficiency at that first band edge state. And then there's a bit of a dip, and then we start absorbing into the second, third, fourth, and then into the continuum of states as we move blue of the band gap. And so as a result, the quantum efficiency of the image sensor for each pixel or the photodetector is basically the same shape as the absorption spectrum of the colloidal nanoparticle that's doing the absorption in the device. And so we can shift this peak around based on the size of the particle. So the really cool thing here about leveraging the quantum mechanical aspect is that depending on the particle shape and size, we can tune the position of that first absorption feature very precisely and accurately. So if we want to tune it to 1330, we can dial it in right at 1330 and just making a slightly smaller particle. So lead sulfide allows us to tune from roughly a first absorption feature from anywhere from 850 out to 2.2 microns roughly. But what's really cool is that we can absorb all light blue of the band gap. So as a result, you can basically have an image sensor that can do RGB, near IR, and SWIR all at the same time, or use filters to do sensing in specific regions of the spectrum. So the thing that's interesting about SWIR is that, you know, there are a lot of really cool applications and use cases that we're exploring for leveraging SWIR imaging. But what's unique and different is that now for the first time, we're offering a SWIR image sensor that is the same cost as a silicon image sensor. So that's pretty unique. And I would say then now we find ourselves in this situation where we're sharing this technology with the world and presenting the opportunity to do low-cost SWIR imaging and identify applications and use case scenarios where SWIR imaging is unique and different and better than near IR and visible imaging that silicon can do. And so looking for opportunities to put this technology into products, and mainly focused on consumer. And so things like resilience to ambient light when you're sensing in specific bands of the SWIR spectrum. Hyperspectral imaging is quite interesting. Enhanced vision through adverse conditions is also interesting. Also, you know, imaging the body, the eyes, the hair, the skin, the face, contrast changes. You absorb a lot of light due to absorption of water in the skin and other parts of the body, which makes it pretty unique. SWIR light is more eye safe. We can image through silicon and plastics. And so I think there's a really cool opportunity to, for the first time, actually do SWIR imaging at large volume, right? Never before could you basically buy millions of SWIR image sensors for the cost of silicon image sensing. So pretty cool. I think as a result, we'll see potentially a pretty big increase in volume and market of SWIR imaging in general. And just to show you real quick, last minute here, we've taken, you know, I think, and many people have SWIR vision systems, and Burion, all the folks in the InGaAs community and silicon germanium community have also taken really cool pictures of SWIR images. But just to give you a sense of what some of the stuff that we've been taking recently using our QD-based SWIR image sensors are just kind of some beautiful photography of natural scenes, trees, landscapes. So the SWIR is kind of a pretty cool new area. Pictures of people and sunglasses and shirts and clothes and paper, and man-made materials tend to look very different than real biological materials. And they really pop out and create a lot of contrast and differences in terms of imaging, and especially the eyes, the hair, imaging the face. You know, there's a lot of really cool opportunities here to leverage this for AR, VR, for consumer, for Face ID, for anti-spoofing, for those types of things that we're looking into. Man-made materials like teeth that aren't real really pop out. You know, being temperature that you wouldn't be able to usually see in the visible portion of the spectrum. Any sort of like presence or lack of humidity is very noticeable and detectable. So rotting fruit or bruising and other things that you would typically correlate to with, you know, different degrees of humidity. Another cool one is seeing liquids like animal pee or just water on the floor that you wouldn't be able to see otherwise, and a lot of lighting conditions really pop out in the SWIR. So think about robots and, you know, seeing imaging, you know, biological stuff that you don't want your robot to run into, like pee and poop from your dog and your cat, for example. And then just imaging through foggy glass and adverse conditions, I think is kind of cool. Imaging through smoke and fog and rain and snow, and, you know, seeing a black ice on the road, and all these types of things start to become really interesting and viable at high volume and low cost using the QD-based image sensor technology. So with that, I'll wrap up, and if you guys have any questions, happy to answer them. So.
Thank you. That's a very exciting presentation, Jonathan. So yeah, please follow up with raising your hands. And I do have actually many questions myself, but let me start with this too. Since you're presenting now in front of the community of quantum sensors, would you comment on the sensitivity of this quantum dot sensors, and could they be pushed towards single photon detection or anywhere close to that? Yeah, no, good question. I think right now we do see an enhanced absorption based on the fact that the particles are quantum confined, and that would just be relative to, you know, bulk lead sulfide semiconductor. But it's not orders of magnitude. You know, it's, you know, a couple factors. And I think going down to single photon, yes, absolutely, that's definitely doable.
maybe not with this specific architecture and sensor system, the way that we've designed it and built it right now, but I would say in general, yeah, leveraging colloidal QDs for sensing in the single photon regime, I think is doable and possible. And then from a sensitivity perspective, I would say, we're pretty similar to where people stand, I would say, in terms of the silicon germanium and InGaAs sensing in the SWIR. There are opportunities to boost that sensitivity, however. So for example, one thing that is interesting, there's a startup in Spain called Curve, and there's a company in the UK called Emberion, and they've been leveraging and looking at putting lead sulfide or other quantum dot mercury telluride materials onto the surface of graphene or other 2D materials, and leveraging that interface to give you a huge boost in gain. So increasing your detectivity, or the amount of sensitivity to light that you can get otherwise. The type of detectors that we're doing, the vertical stack structures, it's very similar to silicon sensitivity, I would say, or InGaAs sensitivity. Nothing too spectacular along those lines right now. So.
Okay. Thank you, Jonathan. I will pass the word to Andreas from CSEM.
Hello, Jonathan. Thanks for the very interesting presentation there. Looking at the last slide that you have there with the figures, I'm just trying to work out if we are at, form factor of mobile phones yet for the detection chip is.
Oh yeah, absolutely. This chip was this sensor and this chip was actually designed specifically for mobile. It's a very small global shutter image sensor, 2.3 megapixel. I think the total size of the chip might be 0.5 millimeter or something like that. So it's an image sensor that's made for mobile. Yeah, absolutely.
Completely compact. Thanks.
Yeah.
So when can we expect these chips in every smartphone?
Yeah, no, good question. I think the challenge right now is that, it doesn't make sense to switch to a new technology like quantum dot image sensor technology unless you can do something that silicon can't, right? If you can enable a new application, a new use case using near IR light or SWIR light that silicon can't do, then it makes total sense, right? So if you're giving the industry a new user experience, a really big advantage by using SWIR light to do something that you can't do in the visible or at 940, then I think this technology will become ubiquitous and we'll have it in all of our phones. But I think it takes time to identify. One, it takes time to let the industry get and receive and play with and assess the performance of a low-cost SWIR image sensor, and then begin to think about what does SWIR light and SWIR image sensing do that I can't do with visible 940 light. And then when you start to answer that question, then it's okay, I can do this, this, and this, and I can do X, Y, and Z better. Or I can't even do X, Y, and Z with 940 invisible, but I can do it with SWIR. So now let's design it into a product. And that takes also a little bit of time. So I think we're at that point where, the industry is just starting to get these evaluation kits and image sensors into their hands. They're taking images, they're understanding what it can do, what it can't do. And people typically aren't very familiar with SWIR sensing, right? What does SWIR light do that you can't do with 940, for example? That's not really known by a lot of people. So it takes time for people to generate data and understand and figure that out on their own, and then design it into an actual product. So we're at the point of people starting to figure out that, okay, SWIR is very different than 940. What can we do with SWIR that we can't do with 940? And let's think about how to design it into products. So hopefully in the coming 2 to 5 years, we'll see more and more use cases and products that would contain low-cost SWIR image sensors. And I think the other thing that's really important to mention is that single chips, right? You can, the Apple products right now use InGaAs chips, and it's a single photodiode, right? So if you want single photodiodes to do proximity sensing behind OLED or proximity sensing in your earbuds or whatever, then you can just use InGaAs because it's a great technology. It's relatively cost effective. If it's a single photodiode, and you only need one per device, and so it's doable. It's feasible. It's great performance, and it's relatively low cost, right? So, but as soon as you want to do image sensing, where you need 2 million pixels or 1 million pixels or 5 million pixels, then InGaAs becomes impossible from a cost perspective. So that's where I think the shift has to happen, where people need to figure out where and when do we need actual images in the sphere versus just single photodiodes in the sphere. So, yeah.
All right. Well, I believe many people in this audience could help out on the side of making these chips even more sensitive. And also, you mentioned these evaluation kits that are, you say, now available for partners.
Yeah. Absolutely, feel free to reach out to me, and we can discuss what your potential use case scenario is and what you want to evaluate, what ideas you have, and assuming it's an interesting application, something that ST is relatively interested in terms of good, decent volumes and going after a market where we would be looking at something interesting from a market size perspective, then I think we'd be happy to work with you, collaborate, and provide you with an evaluation kit and look at how to support that. So
is ST pushing this to longer wavelengths? Is there room in this technology to still push it to longer wavelengths over time?
Yeah, absolutely. So this technology is offered by Sphere Vision Systems and Emberion as an actual full camera system to plug and play, and they cover the full sphere region of the spectrum. So the lead sulfide QD image sensor chip inside their camera can detect out to 2 microns. So at least they're using this same technology to cover 1,000 to 2,000 nanometers. This technology in our hands, we've more focused it on more consumer type applications. And as a result, we've focused in on trying to make really good reliability, good performance, low dark current, high quantum efficiency. And as such, we've focused in on having a first absorption feature at 1.4 micron. So we can detect, a decent amount of light from 1450 blue of the band gap, so down. We could, if there was a need, if there was some application or need where the consumer automotive market needed, coverage out to 2 micron or 2.3 or 2.2 or 1.8, 1.9, for example, micron. That's something that this technology can give and can do, and it's just a matter of increasing the size of the lead sulfide particles and re-optimizing your device for good performance and stability and low dark current quantum efficiency at those rare wavelengths. So, yeah.
Okay. Thank you again, Jonathan, for this very exciting presentation. And please feel free to reach out to Jonathan if you have any response to everything he has just said. With this, I will introduce the next speaker of this session, is Marco Nordmann, the product manager at Qnami.
Hello, yes, let's see.
Hello, Marco.
Hello, Ivan, can you hear me?
Yes, the floor is yours.
And you see my screen. Perfect, great. Yeah, so thank you, Ivan, and thank you, Jonathan, great talk. Yeah, my name is Marco, and I work as product manager at Qnami. As we heard today, quantum sensing offers a manifold of possibilities, from measuring gravity to brainwaves to counting particles. And what is interesting about those quantum sensing is that it leverages what is commonly understood as the weakness of quantum systems. When I think of, let's say, quantum computers, we typically talk about qubits at cryogenic temperatures or space-like vacuum to keep the quantum coherence. But what does the strong interaction with the environment make it a bad quantum computer is what makes it a fantastic sensor to detect very, very small and weak signals. For Qnami, that everything circles around one specific technology, and in particular, those nitrogen vacancies in diamonds. And today I want to focus on the work we do in order to use those nitrogen vacancy centers in a specialist quantum microscope, and how quantum sensing can help to enable energy efficient memory devices. A bit about ourselves and where we come from. Qnami was founded 2017 at the University of Basel by my colleague Mathieu, together with Professor Patrick Malatinsky with the goal to commercialize and scale the concept of NV-based quantum sensors. In 2018, the first sensors were manufactured in an industrialized fashion, and we sold our first sensors. And in 2019, Qnami was the first to commercially sell a scanning NV microscope that was based on this quantum sensor technology. 2021 marked an important date as we received an EIC Accelerator grant to apply scanning NV microscopy to challenges in the semiconductor industry. As of today, we're located close to Basel in Muttenz and are a team of about 20 people. We hold 7 patents around the design of the sensor and the instrument and can access an accumulated 100 years of quantum experience. So what is our quantum sensor, the quantum sensor we're working with? So nature is kind with us as it provides us with a very nice quantum system in the form of color centers in diamond. In particular, we're using nitrogen vacancy centers in diamond, which are associated with the reddish color you see in some of the diamonds. In a nitrogen vacancy, one carbon atom is replaced by a nitrogen atom and a vacancy is left. Trapping one additional free-floating electron from the conductive band forms a negatively charged Nv- defect. And that means we have a very localized electron with a specific quantum state, hence it's a quantum system. And we can also use synthetic diamonds that allow us to tune the doping and crystallographic orientation to shape and leverage, to shape the diamond and leverage existing technologies to our needs. So a bit technical maybe, but those NV centers exhibit some very interesting properties that provide us with 3 main advantages. First, the most obvious one is, of course, the size, right? So it's basically the unit cell of a diamond. And then NV- defects essentially behave like an atomic compass. In their property as color centers, they exhibit a special fluorescence. When exposing them to green light, they show a red fluorescence where the spin properties of the electrons can be directly visible in the optical decay when driving the NV- with a microwave. By collecting the fluorescent signal over the microwave frequency, we can identify the individual electronic states within this decay process. Nature is kind with us again, as we are looking at a single electron with a spin. The so-called Zeeman effect causes one of those electrical states to split under an external magnetic field. The distance between those 2 shelving states or states is what we call an optically detected magnetic resonance dip, depends solely on fundamental constants, and is everywhere in the universe calibrated, self-calibrated, and absolute accurate. For scanning NV magnetometry, then the idea is to implant one of those single NVs into the tip of a full diamond SPM probe. The probe has a small pillar that contains a single defect as close as possible to the apex of the tip. And by mounting this diamond probe to one of the prongs of a tuning fork, we can control the height by moving then this probe over a sample surface and collecting the magnetic information at the same time as the topographic information. If the surface now generates a magnetic stray field, one can collect the contrast information for each position of the sample and measure the distance between those 2 dips. In our picture here, on the left, you see basically the NV pointing along the 100 direction of a diamond, and the contrast of your image gets strong if you would have a parallel, anti-parallel field or magnetic field line along the quantization axis of the NV. Our sensors are called quantilevers and are basically the core of what we do at Qnami. They're manufactured in our own facilities at the Quantum Foundry, and we delivered an instrument where we partnered with Oriba to have a well-established AFM platform to integrate our NV setup. The instrument itself basically is like an atomic force microscope in combination with a confocal setup and a microwave delivery system. All combined with our software, which is called LabQ, one can conveniently access and measure samples with very weak magnetic fields in the order of a few microtesla. Since its launch in 2020, this instrument has helped researchers all around the globe to produce a number of very impactful publications. And here are just a few to mention. Looking, for example, at room temperature skyrmions, multiferroic domain walls, antiferromagnetic textures in bismuth ferrite, or magnetic defects in nanowires. Again, things with very, very low magnetic stray fields, something which you typically would not be able to measure with common devices or other devices you use in metrology. So a real-world application or bringing this technology from research to industry is what we're working on or partnered with IMEC. Thinking about semiconductor and magnetism, certainly the first thing that comes to our minds is magnetic memories. While there are many applications for scanning NV, especially in spintronics, I picked MRAM devices as we already see some of those MRAM devices appear in consumables in everyday's life. If I think of magnetic memory, I have the following picture in mind, right? So there is a magnetic or a magnet with a certain magnetization. And by sending some ones and zeros, I can change its magnetization up and down. Now, to go for large storage density, we want to get these magnets as small as possible, bring those magnets as close as possible, and make switching as energy efficient and fast as possible. And that's a challenge because nature more looks like this, right? So we would switch some ones and some zeros. What you get out is something completely different from what you expect simply due to material defects you have during the manufacturing process. Due to the size of the defect, it becomes defects in those individual bits become elusive during the manufacturing process and very hard to control, which typically results then in very low manufacturing yields and high cost of those memories. Using scanning NV, one can measure easily those individual bits in a non-invasive way and determine the magnetization right after, for example, critical etching steps in the fab. Those images you see here on the right is an MRAM array, and that is quite remarkable because there's no other technology to see a non-contacted MRAM device right when it comes out in the manufacturing. And not only that, not can I only see the individual bits, but I can identify the individual bits and their individual magnetization. And by applying then, for example, an external magnetic field, bit arrays can be switched in a deterministic way and inspect for irregularities in the switching behavior, for example, by looking at individual bits and look at the different contrasts we see in the array. Using then switching statistics, one could allow to, for example, monitor layer thickness or composition during the process and feedback that into the process control within a fab. So quickly summarizing here, what scanning NV allows us is to have a quantum sensing system with that works as non-invasive technology to measure very weak magnetic features. Due to the quantum nature of the technology, offers reproducibility and is a self-calibrated measurement, which is already today accessible through a commercially available instrument. And there are many applications beyond material science, beyond fundamental research. For example, process control in semiconductor industry is just the first where we see how this emergent technology can have an impact on a larger industry. I hope I didn't exceed too much, so I'm happy to take your questions.
Thank you, Marco. This was a great presentation indeed. And yeah, now it's open for questions. Please raise your hands. I will start myself, Marco, by asking you, as everyone else, what this community can do for you.
So, as I said, it's a commercial product, and having reasonable sized laser with reasonable wavelength, as we heard before, is something important. Especially, we are in need of a green laser. There are some available that can be pulsed quickly enough, slightly inconvenient wavelengths, so something more towards 530, 532 nanometers with quick pulsing capabilities, but not that busts the budget would be great to have.
Okay, well received. Now, Devang from GLOphotonics, please go ahead.
Hello, Marco. Thank you so much for a really nice talk. Can I ask a question? You mentioned the really nice capabilities of a single NV center, especially on the tip. What's the possibilities of putting 1 million of these NV centers on that tip and increasing the sensitivities without changing the spatial resolution?
Correct. Well, without changing the spatial resolution would be hard, right? You would have some interaction between those NVs at the tip, and the spatial resolution comes from the flying distance of the NV relative to the surface. So the further you go away, the lower the spatial resolution is. But you're very right, the sensitivity would go up. But one other important aspect of having a single NV is you can make quantitative measurements, right? So if you have multiple NVs, they will go into different orientations within the bulk or diamond lattice, and you would lose, first of all, quantitative data or the information or quantitative nature of the magnetic field. And also, and that is one major benefit of NV, you do get vector information. Once you know in which direction your NV is pointing, you're reading out, you basically get full access to the vector information of your magnetic field, and you can determine structures underlying.
Oh, okay. Okay, thank you.
Okay, and one more question from Marco from Coherent. Please go ahead.
Yes, thank you very much. Marco, thank you for a very engaging talks. I apologize for my camera, by the way, it doesn't work well, so that's why I'm not on camera. So anyway, I was somewhat surprised by your comment about laser needs. I mean, the wavelengths you mentioned in the green, 530 nanometers, is a very common, is a very mature wavelength, and across the industry, the capabilities are between milliwatts to tens of watts. So maybe can you pinpoint a little bit what is the need? Is a very specific variation of this type of lasers, or it should be super low cost? What is that is important for you?
It first of all needs to be able to pulse very quickly, very rapidly, without significant change in the power. So it should be really able to pulse them quickly, and then cost is a very sensitive factor. We do have certainly lasers we can implement into larger instruments, but as soon as you want to have this consumer or this lab grade instrument, costs or things add up, right? So we have this AFM, we have the confocal setup. So then every single dollar that would help saving the cost of goods sold would help then bring more instruments to the scientists. So
okay,
pulsing and price.
Can you give an idea on the pulse duration? Are you talking about nanosecond, picosecond, or something else?
Slightly shorter than nanoseconds would be great. So, but let's say in the single nanosecond range is what we already have, and then slightly below would be great to have.
Okay, thank you.
All right. So thank you very much, Marco, again for this presentation. And I would like to pass actually back to Devang, who was just asking the question. So Devang Naik is a quantum expert working at the GLOphotonics, and he will now share his latest developments with us.
Yes, thank you. Wait, let me just go into. Okay, I hope everyone can see my presentation now.
Good.
Okay, so my name is Devang Naik. I want to start off by, first of all, thanking EPIC for organizing this event and for inviting me to talk, and for thanking all of you for attending my talk. I am part of a new division at GLOphotonics, which is a quantum technology division. Just to give you an idea about GLOphotonics, we are a deep tech French startup in Limoges, France. And although most of our employees are R&D with mainly PhDs, we do have a large amount of industrial capabilities. ISO 7 cleaning rooms, fiber drawing towers, and strategic partnerships with research institutes and universities all across Europe. Our main technology are hollow core fibers. In fact, our founder was one of the developers of these photonic crystal hollow core fibers, and we want to use these hollow core fibers for many different applications. We offer sort of a unique fiber on demand service, where based on your needs, we could provide what you need. We go to standardized fiber solutions, bespoke fiber solutions, but what I want to talk about is our innovative fiber solutions, which is where our quantum technologies really fit in. We have two sort of core technologies: the hollow core photonic crystal fiber and the photonic microcell, and we want to combine these two to create a solution where within the small structures of the fibers, anywhere between 5 microns to 200 microns, we could integrate atoms, molecules, light, maybe even NV centers to be able to give you high atom-light coupling. And this, I think, is one of the key technologies that we could bring to the quantum ecosystem in Europe, high atom-light coupling. So by confining atoms, molecules, whatever, inside these fibers over long distances with guided light, we can get about 1 million-fold enhancement in atom-light coupling. And for us, at least I come from an ultra-cold atoms background. This is one of the main limiting factors that keeps a lot of ultra-cold atoms technology in the lab and not in the industrial applications. We have a series of technologies that have actually been tested. We have a high TRL, and they've been tested by early adopters such as NASA, ESA, Lockheed Martin, and we're always looking for more applications. As I said, our services are very bespoke, so it's something that we have to work with the consumers on. We have a deep tech business model. We want to focus on platform technologies and key enabling technologies. Now, we have many different sort of key enabling technologies, from beam delivery, pulse compression, frequency conversion. And if you want to talk about this, please let me know afterwards, because for the rest of the talk, I want to talk about the quantum technology part. Now, our quantum technology part is divided into three sort of divisions, from atomic clocks to quantum sensors to quantum sources. The main enabling technology we have is the fiber and the capability of incorporating atoms or molecules inside the fiber. We actually have created frequency references with molecules, both acetylene and iodine. We've been able to put inside our halocore fibers and also couple light inside them to create really remarkable room temperature portable frequency references. This is the case of acetylene, which is actually a high TRL level product. We're now moving on to iodine. And one of the interesting things with this technology that we can see is that the strong atom-light coupling allows us to create frequency references at room temperature. Whereas the standard iodine technology, you have to heat up to really hot temperatures, which prevents you from really being able to create something compact and portable. We're able to create signals across the entire frequency span that could actually create for locking and for various different industrial applications at room temperature. Now, we want to go from this to the more quantum regime. And the quantum regime, the workhorse of quantum technologies, have been alkali atoms. Sodium, rubidium, all these atoms with a single valence electron have really driven a lot of interest in quantum computing and whatnot. We want to integrate these alkali atoms inside our halocore fibers and create a new generation of technologies with the advanced atom light coupling. Now, we want to focus on room temperature technologies, not cold for right now. One of the divisions we have inside of our group is a new kind of division about creating portable atomic clocks. These are atoms and light coupled inside the fibers. We want to create a shapeable, compact footprint with low power consumption itself. This is a new and very beginning stages of this project, where we're looking to see if there's people here that will want to collaborate with us on this. As part of this sort of this new direction, we've actually are part of an international EU, at least, a project. It's a FET Open that we've won along with many different institutions all across Europe. And the whole purpose of this FET Open is to develop these halocore fibers into the new quantum technologies using cold and ultra-cold atoms. This is in collaboration with many different institutes around the world. And with this, we want to develop these technologies. One of the technologies we have that actually is more established is our entangled photon source. So using this high atom-like coupling, we could create a very unique entangled photon source for quantum communication, where we could create entanglement between photons of two different wavelengths, 780 and telecom wavelengths. This is actually interesting because now we have a photon that's right at the point of quantum memories, at the same time another photon that can be used for telecommunications. This is a perfect key enabling technology for global quantum communication. The thing that's really close to my heart, because I came from a research background and I worked with quantum magnetometry, specifically for medical imaging, is we want to create the next generation of medical imaging for magnetometry. But unlike the talks that you heard before, we want to work in a high AC regime, megahertz, gigahertz, to create a new type of alternative to MRI and MEG. The other talks you've heard before talk about excitable tissues, neurons that have their own magnetic fields. We want to actually map non-excitable tissues, blood, cerebrospinal fluid, or whatnot, using a version of quantum magnetic induction tomography. I want to thank you for your attention. And like I said, we're really interested in collaborations and getting your feedback on this. So please let me know.
Thank you, Devang. Everyone, please give Devang some feedback and ask some questions that says if there's something you're still missing. Okay, Jacques from CSEM, please go ahead.
Hi, you hear me well?
Yes.
Many thanks for the great presentation. I have some questions sure about atomic clocks. So we are working, I'm at CSEM in Switzerland. you have a huge experience in atomic clocks, and you work in hollow fiber with atoms inside might be interesting. So they will try to do that. Do you think that you will still get sufficiently narrow lines that allow for good frequency stability at short term?
So, okay, you hit upon one of the biggest problems with hollow core technologies. Because it's so small, the effect of the walls will limit sort of the line widths and whatnot. Now, what I can say is that we've been able to form EIT inside these hollow core fibers, and we're able to see EIT with about a megahertz line width itself. So, and this is so using these sort of conditions, we could get a type of atomic clocks with about 10 to the minus 13 level stability. Beyond
with a megahertz line width.
Yes. EIT.
About that.
EIT.
Okay.
Sorry, EIT. I'm using this as a benchmark, sort of.
Yeah, okay.
Which gives you the idea of the effect of the walls that we could have. Now, one key thing that would be important, that would be really nice for us, is to develop new coating technologies that we could use to coat the inside of these fibers. Because the normal glass vapor cell technologies have these amazing coating technologies, starting with paraffin, that allows many different collisions. This would be an enabling technology which can really help the hollow core fibers, not just in terms of clocks, but also in terms of quantum sensing in general.
Because it's a room temperature one.
Yes, it's a room temperature one. However, as part of the CRIS3, this European Union Consortium, we're developing cold atoms, so about 100 microkelvin technologies with this itself. We have worked with Singapore and also my old institutions where we developed sort of dark state cooling, which we applied inside the fiber itself. So the idea here is we could do stroboscopic cooling inside the fiber. Cool, in which case we have 20 milliseconds before the atoms can interact with the walls, to where we could do the quantum sensing.
Might be good to keep in touch.
Oh, I would love to, yes.
Okay, thanks.
All right, this is the spirit. So, well, thank you very much then for your presentation again, Devang. So now you have already one partner potential to consider. And with this, I would like to pass the word to the last speaker for this session, is Enrico Casamenti. He's an R&D engineer at FemtoPrint.
Hello, and thanks, Ivan, for the introduction. Just start sharing my screen. All right, can you see it?
Almost there. Yeah, you're good to go. Thank you.
Okay, great. So good afternoon, everyone. And thanks again, Ivan, and all the EPIC organization for inviting us. So it's my pleasure to present you something we are doing at FemtoPrint related to quantum sensing. So I'm Enrico Casamenti. The talk for today is entitled Glass 3D Micromanufacturing for Monolithically Integrated Quantum Devices. So FemtoPrint it's a Swiss company. We are a contract development and manufacturing organization, and we are focused on 3D microfabrication in glass. So we were founded in 2013. We are now growing quite rapidly in the last years. So we are now more than 35 people. And as I was saying, we are located in Switzerland. The headquarters is near Lugano in Ticino. And we have our business unit in Photonics, which is actually in Neuchâtel. And what we offer is a technology which is very versatile and diverse. So it's based on lasers, but it has many possibilities. So we start with the freeform manufacturing in 3D of glass, but we can also inscribe inside the glass optical patterns and waveguides. We are able to weld different materials, mainly glass with glass, but also glass with silicon. And then we can drill and dice different kind of shapes. We can do very, very precise fiber holder, fiber aligners. We have surface treatments for mainly to increase the roughness, so for freeform optics. And then we also perform metal coatings and ablation to insulate some electrodes and create 3D electrodes arrays. All these with very high performances, especially with fused silica. So there we can have a resolution around the micrometer. and the surface quality, it's rather good after the machining, but can also be improved further with the surface treatment to below 20 nanometer of average. Now, with all this, our main focus and our main action in the quantum field is related to three-dimensional glass ion traps. And I think most of you maybe know even better than me what ion traps are and what they are used for. So one of the main applications is quantum computing, but in fact, especially this kind of three-dimensional ion traps are extremely stable. So it seems they can have a very good application in precision measurements and frequency standards for atomic clocks, but also for spectroscopy. So here, for this presentation, I prepared like 3 examples of a few works we did in collaboration with some universities. So we don't prepare the design, so we are a manufacturing company. But these, for example, are from ETH in Zurich. 2 different designs of ion traps, and those are a few layers which are assembled together very precisely with a micrometer precision. And we can focus on the B, so the one on the right, sorry. And here we have a few more images. I will try to explain. So here on the right is the full assembled trap. So it's a few layer stacks, and it's already assembled, and I think also wire bonded here to the PCB. But then in this trap we have different features and things that we were able to add thanks to our technology. So for example, in the core layer, so the central one, they needed this kind of protrusions to break the symmetry of the field. So we could create easily this protrusion here, or we added this through wafer via. Another important feature they wanted was to have the fiber connected inside, and so already assembled so that they could have the light illuminating the core of the trap. So here you see it's a squared groove, thanks to which we could precisely place the fiber. And then we prepared this mirror surface that was then polished and coated so that the light could go vertically inside the core of the fiber. And as I was mentioning before, all these traps are multi-layers. So what we developed is, well, actually it's not new, but it's the use of self-assembled geometries. And since we can work easily in 3D, then it's easy to implement them. And with that, we could really precisely stack layers on top of each other, and then increase even the three-dimensional capabilities of the technology. And all this is with the micrometric precision. And as you can see, also there were some coatings in between, so we can also perform the coatings of different metals, both with evaporators or sputtering, and also with the possibility of placing hard masks in some places. Another example I'll show you quickly is this work with the University of Innsbruck, and here it was a bit more complex. I'm also not an expert of this, but it's a panopticon device. So it's this combination of an hemispherical mirror, the ion trap, which is what we did, was needed here to basically place a single ion of the barium inside the hemispherical mirror. Then you have this spheric lens, and you use this device to basically study the inhibition and enhancement of the spontaneous emission of this ion. So this will add few interesting applications for spectroscopy mainly. And just going forward, one thing I wanted to show is this wafer we produced for another university from Sussex. And just to show that we, in fact, I was presenting a lot of die level, so just devices, but in fact we are working and moving always more to wafer scale production. So here there's a small example of what we are doing. So placing few ion traps on the wafer. This is a 4-inch wafer, but we can move easily to 8-inch or even more. And then the other big advantage is this optical integration. So I picked few examples, and again here you can see a set of holders for fibers that is a set of V grooves here to place them. And I mentioned we can write waveguide inside the glass in 3D. So this one is a straight one, but we can have it in the 3-dimension moving. And the other interesting thing is that we can couple, like being the fiber, but also preparing the lens with the surface treatment to have a nice lens to collimate the light inside or to outcouple it. So all this can be done with our technology, which can enable really monolithic design. And with this, I move to this slide, which maybe it's not the best to present, but I rather prefer to leave it here while if someone has some questions. So I can hand my talk saying thank you for the attention, and I'm here for any questions you have. I put back this slide.
Yeah, thank you for putting back this slide. I think it's one of the most important ones for our meetings. So does anyone have questions regarding to this slide or the previous ones?
Yes. Is there do you think this would also work with a silicon nitride wafer? A wafer that had a coating of silicon nitride, could you manipulate and etch and so on that surface material?
Sorry, do you mean if we could manufacture in this way in 3D the silicon nitride?
Yes.
So I'm not aware of work done with femtosecond lasers with the silicon nitride. I'm sure you can work other kind of glass, but I'm not sure about the silicon nitride because this technology is based on linear absorption. So what we actually do is we are inscribing with the laser and then modifying locally the glass, so the material, which means the material is modified only inside the focal volume, but not anything anywhere else. So there's no ablation. And then after you have an etching step to remove the material that was modified by the laser. So this was developed in fused silica. That's the main material that was studied. I'm sure I know that you can transpose this to other kind of glasses, some borosilicate, aluminosilicates. But again, I know there have been some work on diamonds, but mainly for waveguide writing and not really for etching. There's a lot of research going on to apply this kind of 3D structuring to other materials indeed.
Thank you.
Yeah, no problem.
Okay, that's a good explanation, Enrico. Anyone else? Well, if not, I think it was very informative on your part, Enrico. So thank you for concluding our session today. I will just follow up with a few slides of my own. So just to remind you, so this was the online technology meeting provided by EPIC on quantum metrology and quantum sensors. I'd like to thank again all the speakers we have heard today. So Katrin, Vincent, Menoret, Andreas, Schürzinger, Steckel, Nordmann, Devang, Naik, and Enrico Casamenti. So you have now this pop-up poll to give us some feedback about the meeting you have seen today. And I would also like to remind you that this was made possible thanks to the whole team of EPIC that you can see on your screen now. And also reminding you that EPIC, the European Photonic Industry Consortium, is always there to support you with technology consulting and providing market reports, networking opportunities, providing access to new markets, and providing mentorship support, as well as HR support and support with investment. Now, this technology meeting is one of a series of online meetings that will take place in 2023. It's already announced for the first semester of the year. We'll follow up with a meeting on micro LEDs for automotive applications in March and photonics for climate change monitoring in April, as well as additive manufacturing, agriculture, and laser welding and photonics for wearables. Apart from these online meetings, we now switched a lot to organizing offline or face-to-face meetings. The next opportunity to see me and my colleagues will be at the OFC, where EPIC organizes several networking opportunities during lunch and during receptions, as well as the famous EPIC members run. Now, end of March is the annual general meeting of the whole EPIC assembly, which will take place in Helsinki in Finland. And the first two offline events of the year is the EPIC meeting on fiber sensors at the headquarters of HBK Fiber Sensing in Porto, and the EPIC meeting on photonics for AR, VR, and mixed reality at GLOphotonics in Jena. Yeah, please feel free to join us for the events that are of your interest. And with this, I'd like to just one more time thank the sponsor of this event, the PI Imaging, and wish all of you the very good continuation of the day. Thank you very much.